In this lecture, I'd like to talk about energy diagrams. Energy diagrams are a plot of potential energy versus position S. As we saw, potential energy is associated with a position of the object, and we also saw that associated with each potential energy there is a force. For example, gravitational potential energy, there's gravitational force. With spring, associated with spring potential energy, there is spring force. Gravitational potential energy is of course proportional to the position of the object relative to a reference level, and the spring potential energy we saw is proportional to x minus x naught squared, the amount of compression or stretching that the string has squared. So each force leads to potential energy, and an energy diagram is a plot of the particular potential energy versus the position. For example, in the case of gravitational potential energy, UG, we of course plot gravitational potential energy versus Y, and if we consider an object's potential energy in the Y direction, if we call this our zero level, an object which is at y equals h, for example, has a potential energy of mgh, as we saw before. So at y equals 0, the potential energy is 0. As the object rises in altitude, then its potential energy goes up respectively till this is mgh. So this point here corresponds, this point up here corresponds to the position y equals h. Now let's say that we actually start with the object at the ground level, and we throw the object upwards. Therefore it has some initial kinetic energy, which is equal to 1/2 of its mass times initial speed squared, and it goes all the way to its turning point. That's where velocity is 0, of course, and after which it turns back and falls back to the ground. So the initial UG initial is 0. Now UG final is simply mgh. K initial kinetic energy is 1/2 of mvi squared, and final kinetic energy is of course 0 because final velocity, final speed is 0. So the total, if we plot UG, gravitational potential energy, versus position y for this object, we end up with the straight line that I have up here. Okay, and notice that the object starts at 0 potential energy, and as it goes up along the y-axis it gains gravitational potential energy till it reaches its maximum level, after which the object turns around, and as it falls back to the ground, then it relinquishes its gravitational potential energy till it's back to 0 again. So this level up here is the maximum energy that the object, the maximum potential energy that the object can have. And at this point, which is our turning point, our kinetic energy is 0, and at this point the kinetic energy is maximum. At the turning point our gravitational potential energy is maximum, and down here our gravitational potential energy is 0. So in a plot of potential energy versus position, you notice that there is a maximum level for energy. That's the sum of the two kinetic and gravitational and potential energies, and where the object's potential energy line crosses the maximum energy level is our turning point. That means that an object cannot exist above the total energy line that it has. Turning point. At turning point, the object must turn around and follow the path downwards. Now, the potential energy at any other position, let's say here, the potential energy is of course given by the graph, which is this level right there. So this amount here is the potential energy that the object has at this particular y value. So let's call this y1, and its kinetic energy is given by the remainder of so that's kinetic energy 1. So kinetic energy 1 is equal to total energy that the object has, which is this level right there. Oops, sorry. Minus potential energy 1. Okay. At a different position, let's call this y2 right here. So if this is y2, then you notice that potential energy is decreased or is less than position y1, whereas the kinetic energy k2 is greater. So as the object is falling back to the ground, its kinetic energy increases as it gets closer to the ground, which means that the speed is increasing, which is what we know happens in a free fall. Also, when we throw the object upwards, it has maximum speed to start with, and the speed decreases as it gains height till it reaches the turning point when the speed is 0, and it has maximum potential energy, and then it turns around and falls back. So this energy plot actually tells us a lot about what is happening to the object. So if I were to draw generic potential energy versus position plot, so this is potential energy, that's position S, and let's just draw something like this, for example. There. Okay. Now, and let us define the total energy level to be here. So that's E. Now, as I said, the first thing that you need to notice is that where the total energy line and the potential energy lines cross, that's this point and this point. These are the turning points. Right. That means that the object, as it moves about the S axis, when it comes to this turning point, turns around, comes back, turns around, goes back, turns around, etc. So it goes back and forth in between these two turning points. The definition of turning point is where the object reverses its direction. Next thing to note is that an object, well, what we have here is a plot of potential energy. So if we were to take a look at positions, let's take a look at positions A, B, let's look at position C here, and perhaps position D here. At position A, the potential energy that the object has is given by the graph. So this is potential energy at position A, and what is left till the maximum energy level, of course, is the kinetic energy A. Similarly, here we have potential energy at position B, and this is kinetic energy at position B. So notice that at the minimum point for potential energy, we have maximum kinetic energy. That makes perfect sense, since total energy E is equal to kinetic energy plus potential energy. So if potential energy is minimum, that means kinetic energy is maximum. So you know that at position B, the object has maximum velocity. So the object is moving fastest at position B, according to this chart. At the turning points, speed is 0. We also know that. What else can we tell from this position versus potential energy versus position plot? Well, the other thing that you can say is how much force is acting on the object along the S direction. Fs, which is the force acting along the S direction, is equal to the negative of the slope of the potential energy versus position curve. So this is a very useful relationship to note. So if we were to look at the slope of these lines, for example, at position C, we have a positive slope, which means that the force at C is a negative force acting on the object, whereas at position A we have a negative slope, so force at position A is a positive force acting on the object. That makes perfect sense as well. A positive force along the S direction leads to the object speeding up, going from position A to position B, as the kinetic energy Ka and Kb imply, of course. Now at position B, the slope of the line is 0, which means that at B, force B is equal to 0. So there's no force acting on the object at position B. In fact, position B corresponds to the minimum. Actually, that's an equilibrium position for the object. And also somewhere along here in this range right there, we also have a 0 gradient, which means that there's no force acting on the object either. So you can say a lot about what is happening to the object by looking at the potential curve versus potential versus position graph for the object. Remember that force is equal to the negative of the gradient of the curve. You can note the turning points where the object reverses direction, as well as noting the kinetic energies and potential energies at different positions. So for example, if you know that the object has some total energy, then knowing the potential energy at any position s, you can calculate the kinetic energy or the speed of the object at any other position. You'd be making use of this further down in the course. Now if you look at the spring force, F spring was equal to minus K x minus x naught. That was Hooke's law. And now if we said that Fs is also equal to negative of the potential energy, so if I write this in an integrable form, I end up with this. Substituting for Fs, I have minus K x minus x naught is equal to minus dus. Integrating both sides in between initial and final values, we end up with 1/2 of K x minus x naught squared is equal to us. That's the expression we had for the spring potential energy so far. So if you were to plot the potential energy versus position for a spring, let's note where our x naught is. That's the equilibrium position for the spring. That's the potential energy of the spring. So we actually will have a parabolic curve which is 1/2 of K x minus x naught squared, proportional to x squared. I apologize for the crooked graph, but I hope you forgive me for uneven drawing here. So once again, the potential energy that the spring has is given by the graph. So these are US values, and if we say that the total energy is limited to this value, then the kinetic energy that the object has at any position is simply the remainder of E minus US. And notice that well, that's okay, I'll leave it at that. Now if we look at the slope of the line is positive when the extension is positive, which means that the force is negative when x minus x naught is positive, which is what we discussed earlier. If you stretch a spring, that's a positive extension, the force is in the negative x direction, i.e. a negative force. Similarly, in this range where the slope is negative, that implies the force is positive. So when x minus x naught is negative, then the spring force is in the positive direction. Now if you have an object resting on a spring in the vertical direction, so this is our y direction, and we have an object M compressing a spring. So let us go ahead and note the equilibrium position for the spring. So in this case that's y0, that's the equilibrium length of the spring. So the object is compressing the spring to some initial value, and then when we let go, the spring stretches to its natural length and the object is shot upwards with some final velocity. Okay, so in this case we have both gravitational potential energy change and spring potential energy change, as well as kinetic energy change. So we defined our zero level for spring potential energy, that's y naught. I'm going to define this value also to be my ug naught. So at y naught, ug is also 0. So now let us, this is our initial value, that's our final value. Kinetic energy initial is 0. ug initial is mg y initial minus y naught, and us initial is 1/2 of k times y initial minus y naught squared. Okay, so this is our initial values, and our final values. K final is 1/2 of mass times velocity final squared. ug final is 0 and us final is 0. Now in the absence of friction forces, we have k initial plus ug initial plus us initial equaling k final plus ug final plus us final. So what we have here is 0 plus mg y initial minus y naught plus 1/2 of k y initial minus y naught squared is equal to 1/2 of m v final squared. Therefore, knowing y initial and y naught, we can go ahead and calculate what the final velocity of the object is, of course. So in this scenario, if we rearrange things a little bit, you see that, well, first of all, y initial minus y naught is a negative number because y initial is below y naught. So here we have minus mg delta y plus 1/2 of k, well, let's just call this delta y squared, is equal to 1/2 of m v final squared. So notice that if in the horizontal, if the spring were compressed along the horizontal direction, then all the spring potential energy would have been transformed into kinetic energy. But since there's also change in gravitational potential energy involved, the final kinetic energy is reduced by this amount, which is the change in the potential energy. So some of the initial spring potential energy goes into gravitational potential energy, and the remainder speeds the object in the positive y direction. If we take a look at the energy diagram for a spring which is compressed along the vertical, this is in the y direction, this is u. Now there are two potential energies involved, so we have straight line for ug, that's gravitational potential energy, and if this is y naught, we have a parabola for us. So total energy u is equal to spring potential energy plus gravitational potential energy, which is equal to spring potential energy is 1/2 of k y minus y naught squared plus mg y minus y naught. Okay, so now if we want to note where the new equilibrium position for the system is, we simply find the minimum of this graph. So by the way, graphically, if you add these two curves, you should end up with something that looks more or less like this, which is a lopsided parabola which has a new equilibrium position. Let's call this y min. Right? So this new position, a new equilibrium position, is at y min du dy is 0. What is du dy? Du dy is differentiating this expression up here, we end up with k y minus y naught plus mg. Setting it to equal 0. This is at y min, of course. We end up with y min equaling y naught minus mg divided by k, which means that y min is shifted leftwards from y naught. That makes sense because if a spring's natural length is at y naught, if you were to place a mass on top of it, then the new equilibrium position y min is downwards in the y direction, or in our plot here is to the left. So it's shifted leftwards, and the amount by which it is shifted depends on the stiffness of the spring, inversely dependent on the stiffness of the spring. So the more stiff a spring is, the less shift we are going to have to the left, and it's directly proportional to the mass of the object, both of which means the massier the object is, the more of a shift is going to cause in the minimum position for y. So please do remember that the way to find the new equilibrium position for the system is simply to look at the derivative of the potential and finding and setting it to 0. That will give you the new equilibrium position for the system.